Welcome again. So today, as you all know, we have a bootcamp, a software bootcamp by QuEra, and Pedro Lopez is over here to give that session. We have been hyping about this particular training program for a long time, and I know you all are particularly excited about the training bootcamps. So this is your chance to actually learn about stuff, especially on the neutral atom side, hands-on. We had some really amazing sessions yesterday as well, but they were more on the theoretical side where David DiVincenzo and Jeff Thomas explained what neutral atoms were. But today you would actually get to know about more practical knowledge about neutral atom quantum computing by Pedro himself. So a bit about Pedro. He is a quantum advocate currently at QuEra Quantum Computing. He holds a PhD degree in theoretical physics, and his research career spans Brazil, USA, Canada, and he has explored a variety of topics ranging from quantum matter to topological qubits. He is very passionate about communicating quantum computing at all levels, whether they be helping customers, whether developers, and yeah, he just is really amazing about spreading knowledge to all sorts of people. So yeah, this is a great chance for you to learn from him directly. Pedro, the stage is yours. Please take it away.
Thank you so much for the introduction, Vardan. This is very kind, and welcome everybody. And nice to see you. It's a very crowded audience, so I'm very happy to see. I hope that I'll be able to answer as many questions as possible from all of you or most of you. We will be going through a set of this activity is gonna be separated in two lectures, basically. One on basics of quantum computing with neutral atoms, and the second part on a specific application on optimization. Just to keep things concrete and bring you, to be able to go from, I like to call it 0 to 1, really. So from a starting point to being able to deploy one useful application, right? And then from there, you can take it away by yourselves and really explore, whatever you want to explore, really, okay? So please stop me at any moment. I will go and share my screen, and we'll start chatting just quickly about where to find these materials and how to install everything. So I hope that you were able to get the systems running for you before the session started. So if you go on GitHub or on Google and you just go for GitHub QuEra and you look for the repo QuEra education, and I can, I guess, simply paste this on the chat just for the sake of making this easy. Here you will find our building set of documentation and educational materials. So this is work in progress, but we have quite an extensive set of notebooks and PDFs for presentations and handout materials that you can access. And in particular, most of the materials, they're accompanied by Jupyter notebooks. So you can see here, there's a Jupyter notebook that runs using a software suite called Blockade with a Q and no U, as quantum things go. So Blockade, again, you can just Google for Blockade, but I will also paste this on the chat. It's not so hard to find it. It's a software suite. It's open source, but it's maintained by QuEra right now. And it works on a language called Julia, which is efficient, more efficient than Python. It starts lists on 1, not on 0. You can judge if you prefer that or not. I prefer that. I always start counting with my single fingers. So anyway, the point is, Blockade is a very efficient suite for emulating the behavior of a neutral atom quantum computer. In particular, the quantum computer called Aquila, which is the machine that we, QuEra, have on the cloud. So anyone can actually access Aquila via the Amazon cloud, the Braket service. And Blockade also can be used to submit jobs to Aquila. As long as you have an AWS account, you can do that. So Blockade can be installed on your own laptops or computers. There's a an explanation of how to do that. It requires you to install Julia and install iJulia so that you can operate it on Jupyter Notebook in an interactive way. So I encourage you to do that. But to keep things simple, our friends from QBraid at Chicago have provided us with a key called QuEra_WOMANIUM 23 that if you enter the QBraid platform, let me see if I can just do it myself here.
Yeah, let's do this part in steps all together, so everyone get along soon.
So you just enter the QBraid, so QBraid.com, and then you either sign in or start now. So if you have not signed in, I encourage you to sign in. And then if you're going to be brought to this page where you can click Manage. And you can find this section that says Access Key, where you can paste the WOMANIUM key that I will remind you again is QuEra WOMANIUM 23. And I'll paste this on the chat. And if you arrive here successfully, you will be able to come to, I believe that the place is in the lab. So let me go back. You're going to see that you have a blockade CPU, and you'll be able to launch it via the launch lab. Oh, no, I already got a server running. Yeah. Yeah. So you should just be able to extract it from here on. And if you get that, actually, that's the easiest way. Once you submit you activate your key, we come back to our Julia, to our GitHub page, and you have a nice button here. That's my favorite button these days. You just come this button and you press launch, and it's gonna launch the whole set of educational materials on QBraid for you at a single click. So this is actually really my favorite button. We are going to be going through the materials from section 1 and 4 today. I do encourage you to learn all the other materials as well. They don't have a necessary structure. I mean, ideally you will follow them in order, but as long as you do section 1, you can follow all the others without too much trouble. And you have a session on Rabi oscillations and some standard physics types of experiments that you can do. There are sections on how to submit jobs to the Racket service, which is something that you probably cannot do via QBraid. You would need to install Blockade on your own machines to do that. The session on maximum independent sets and optimization, which is what we will go through today. And an interesting session also on how to run Blockade on high-performance computing centers. So if you have GPUs, if you have multi-core, you can use Blockade much more efficiently because it was made for that. So I hope this gets us going. I unfortunately won't be able to go through this very slow because time's of the matter, and we have a ton of material, and I hope that we can actually cover most of that material because that's what will really matter. But
shall we take 1 minute, Pedro, to see if there are questions about the QBraid launch, so everyone is able to go ahead? Please, everyone, try first with the access key, launch lab, and then return to the GitHub. Scroll all the way to the bottom where you see QBraid launch and click launch there. Okay, and David points out, change the CPU to Blockade CPU before you click launch lab. Could you show that again, Pedro, where we should do that?
Oh, yeah, that was not appearing for me because I'm already, but I guess this is it.
Right.
So you just click on the blockade here in the center.
Okay, very good.
But again, you don't need to worry about it. Okay, so as long as you come straight to our GitHub page, this should launch on a blockade CPU.
Okay. And Dawal asks, where do we add the token?
So to add a token, you go into your plan here, you click on manage, and then access key. And then here's where you paste it.
Yeah. Viraj asks, what is the process on GitHub? I joined just 5 minutes ago. That is not important now, right? As long as you just read it.
Yeah. Don't
down.
worry. Yeah, don't worry too much about how to operate on GitHub. It's more complicated than developers tend to accept. Okay.
Right.
So.
Right. Sarah asks, how do we launch from GitHub? Go to that README page, of which we show the link, scroll all the way down, and there you see QueRa launch. Click that launch icon. Some people have the server is starting up and then spawn failed. Yeah, maybe that just takes some time, Nasser advises.
Yeah, so this might take some time, okay? In particular, for the first time, that might take some time because Blockade is a heavy package. So don't worry about it. We will keep going. We'll go through the contents. And if you're doing this right now, hopefully by the time we are done, that will be gone. And we will see. In any case, we'll have homework activities. So even if you don't operate them right away, you can do them later.
Great.
Sounds good.
Vardan will also be on Discord now to help with questions.
Lovely.
I'm excited.
So in this case, I will move to the contents so that we can try to cover as much as possible. Sounds like a plan? Okay, I got a thumbs up, so launch. Welcome to our session 1. This session is going to be on the basics of quantum computing with neutral atoms. And usually this goes really through the intricate details of how the machine works, our machines work, or at least our first machine, how it works, because I believe that it's kind of relevant to know exactly what's going on with these atoms when they're computing. And I emphasize that some previous knowledge of physics is necessary for this tutorial. Some previous knowledge of quantum computing is definitely welcome for this tutorial. Okay, so if you can't follow everything that I'm saying, don't worry. We ask questions. We will get you as much speed as possible. And operating the blockade, it's not going to require you to know much programming or even much Julia. It's really, everything is very well packaged. But I want to emphasize that there's going to be a steep learning curve here, and I hope to ease that steep learning curve for as many of you as I can. So given that, I have some house rules here. And if you really want to get the maximum out of this activity, I do encourage you to keep your videos on. Okay, so I know that that might be a little challenging in some situations. There might be some connection limitations, but I do encourage videos on because that will keep you engaged. It will keep me being able to see how you react. So I encourage that if you can. Mic's muted unless you want to speak, but I also encourage you to unspeak yourself and just reach out and ask your questions. We will try to manage so that this doesn't get overwhelming. We have a very, very large cohort here, but it's okay. And yeah, so given that, interrupt me. You use Discord, use the chat, or raise your hand. We will. The goal here is to get you to learn as much as possible. Given this, why we are here, right? So we are here to learn about neutral atom quantum processing, and this is the cool technology to be thinking about right now. I am biased, of course, but I gotta say that there have been many reports in the literature of how neutral atoms are coming as a dark horse in the race for quantum computing. A few years ago, no one was talking about doing quantum computation with neutral atoms. Everybody was talking about ion traps and superconductors, and then maybe some photonics. But right now, this technology is coming up. The first public machines are already accessible. Again, QuEra has, to date, it's the only publicly accessible machine. But with this technology, we can actually pack a lot of qubits together. So Aquila, our machine on AWS, puts up together up to 256 qubits, and I will explain it's why up to. It's something that's going to be very clear pretty soon. But these are the largest quantum machines available to the public today. Okay, so there are other machines that are kind of privately accessed that may be bigger, but publicly accessible, this is the largest that is out there. And these machines, they have some very interesting and efficient control for the qubits and some flexibility for problem encoding that really needs to new ways to do and think about quantum computing. So it is very, very, very exciting. This is really ramping up. The technology is really drawing a lot of attention. So I hope that we are all excited about it. And if that's the case, I will start with telling us what are going to be the learning objectives of our first session. So by the end of this first session of today, which is going to take about 1 hour, 1 hour 15, you should be able to explain how neutral atoms can be used as a platform for quantum computing. Hopefully the sessions that you heard from yesterday. So I heard that there were some sessions by Jeff and people that are much more knowledgeable than I am even about this. So I'm pretty sure that we'll be able to check this box very easily. We will be able to distinguish analog and digital, or what's called gate-based quantum computing. It's something that is very important for this kind of platform. We will define what are field programmable qubit arrays and exemplify what are the advantages of using field programmable qubit arrays for doing calculations. And I want to get you prepped for if in the future you want to be able to submit jobs to Aquila again, our machine on AWS. So you'll be able to learn what are the programming range. So what are the control parameters and what are the limitations of service for this machine. 4 learning goals, and we will go through them step by step. Very well. So what is a qubit? How a qubit works in a neutral atom quantum computer? So in our machines here at QuEra, today we are using rubidium. If you're forgetting where rubidium lies, it lies in the first column of your periodic table, kind of downish, the center down, lower part of your periodic table. And the fact that it lives on your first column means that it behaves just like hydrogen. It's hydrogen, okay? For all that you care, think of hydrogen. It's hydrogen. It has 1 electron that is kind of free for you to interact with. It's just heavier. It's heavier, so it's easier to hold in place, to trap. Okay, so neutral atom quantum computers, they operate by holding atoms with laser tweezers. So it's a tweezer. It's like the one that you use to pick eyebrows or something. And these lasers, they are not straight, right? They have a waist. So this waist you can use to hold things. People in the biology, biotech community, they use that to hold cells and organelles. We hold atoms. We hold rubidium atoms. And given that these atoms have 1 electron that is free to move, we can play with that electron to create a qubit. So a qubit is, as you may have been developing some expertise, it means roughly 2 well-defined quantum states of a quantum object. And in this case, it's this electronic cloud. This electronic cloud, when you leave it alone without doing anything to it, it sits in what we call the ground state. And if you remember your orbitals, this is a 5s orbital. And you get to pick what's the second one. There are many, many, many options, roughly infinite of them. We pick an orbital for exciting this electron that is called a Rydberg state. So a Rydberg state is any highly energetic orbital of the atoms. So you shoot laser light, this electron captures that laser, it spins bigger in a classical picture, it's gonna puff up. Okay, the faster, the more energetic that this electronic cloud is, the larger this atom becomes. Okay, any state that is very, very highly energetic is called a Rydberg state. It's not ionized, but it's almost ionized. You almost remove the electron. Okay, so if 5s is the ground state on Aquila or a machine, this electron goes to a principal quantum number equals 70, 70. So from 5 to 70. And this atom goes from angstrom, so 10 to the minus 10 meters size, to roughly a micrometer scale when it puffs up. And what happens when it goes to a micrometer scale is that it becomes strongly polarizable. So it reacts to electrostatics, to electricity close to it. And when that happens, two atoms that are close together, they start seeing each other if they are both excited to this Rydberg state. This interaction is called a van der Waals interaction. You might have seen this in some chemistry. And if you have heard of graphene and how graphene layers, they stick to each other, that's what we are talking about. It's the same type of force. And so it's a type of force that happens between neutral particles because they can polarize each other and their dipoles induce dipole moments in each other. So those are the two states that are going to form our qubits, a ground and a Rydberg. What does the process of operating this look like? You will not need to know this. You will not need to even see this, but it's nice to know what happens whenever you submit a job to Aquila. And I'm going to tell you what's going to happen. So what's interesting about neutral atom quantum computers is that every time the user calls for a job, we make a new chip. We make a new register according to the desire of the user. It's very different from the chip of your laptop that somebody printed in a factory at some point, right? And now it's done, it's stuck on your laptop. It looks what it looks like and you will never change it, okay? Here, there's a communication, a dynamics that happens between the user and the QPU, the quantum processing unit, according to the desire of the user. So in this case, what happens is the following. First, we are going to have a cloud of these rubidium atoms that's going to be cooled and held in space by something that's called a MOT, a magneto-optical trap. It traps things, in this case atoms, via optics and magnetism. So it's a mix of magnetic coils and some laser lights that holds these atoms in place, forms a little cloud and pulls it down. Then there's going to be a set of other lasers that are going to form a pattern. That pattern is determined by the user. And I just received a question here. Doesn't noise ionize if it's almost ionized? No, it's not that close to ionization. So there's really no ionization happening here. So the atoms, they keep the electrons. So coming back, we generate a cloud, we trap it in space, we shape some set of laser beams into a pattern that is what a user looks like. And we shine that laser through this cloud of atoms. So here what you're seeing, every pink dot, pink purple dot, is an atom, a single individual atom that is being held in place by one laser beam that here is shaping this kind of squarish rectangular pattern. Now, this process is stochastic. This means that it's not deterministic. So some atoms get stuck in place, some atoms do not get stuck in the place that you want them to be. It's nice that you never get more than one. It's either 0 or 1. If there were 2, they collide and boom, both of them fly away. So that's sometimes nature is against us when we are trying to make a quantum computer. This day, nature was in our favor. If sometimes it got 3, sometimes it got 4, sometimes it got 5, we would be in big trouble. Here, it's 0 or 1. But it's not good enough. Imagine if your chip, right, your laptop, only 60% of it had transistors in the right place. That was not going to work. So we have to do better. So we image that thing. We figure out where there are atoms, where there are not atoms. And this sends a set of coordinates back to the CPU that's going to program a set of mobile lasers that can actually take atoms from other outside regions. And this reservoir of extra atoms, we can use it to refill things in the pattern that we want. And here, what we learned is that the user actually wanted these sets of 3x3 squares of atoms for whatever reason. The machine images that again and initializes a set of pulse sequences. And only now you are doing a quantum computing process. Here is where some lasers are going to act on these atoms and actually do a calculation according to what you need. So there's a big process here that is shaping your register, and then you do the calculation, and in the end, you image it. And here the user was trying to prepare this kind of cross symbols. Okay, so this is just an example. The user could be trying to do many other things. In this case, the user was trying to do these cross symbols in each of these sets of 3x3 clusters of atoms. And this is cool. So notice the most important part of this is this part here, the sorting part, where the machine is going to put atoms individually in any way that the user wants. And this is something that you will not get in any other quantum computer technology. Okay, so this is something, everything else, be them ion traps, be them superconductors, they come stuck the way they come. And this is fun because we, as you see later today, we can use this to do specific calculations. So moving to a cartoon, what is a register going to look like? Well, this register is going to look like something like this. It's going to be a set of atoms. The atoms here are the blue dots, blue circles or spheres. They're going to live in a 2D plane. No, you cannot do in 3D. You can do in 1D. You can align them in a single line. But generally, it's going to be a 2D plane. You see that there's some laser light coming from above here, outside of the plane. And these are the lasers that would be holding the atoms. And you see that there are some atoms that have this greenish, larger circle. These are the atoms that are being puffed up to interact. They're being puffed up by a laser that shines in the plane of the atoms. And this is something that is important to realize. All the atoms are going to be controlled by a single, it's not technically a single, it's a little bit more, like 2 or 4, but that's just for technicalities. But it's a single laser atom that shines in the plane of the atoms. And all the atoms receive the same laser, and all the atoms are controlled at once, which means that there's no bunch of cables that go in this system. It's everybody's controlled with very few control lines. Let me take a moment here because there's a question in the chat.
Yeah, let me start with a couple of quick questions, Pedro.
Yeah, let me start with one in the chat here that somebody wrote directly to me. So somebody asked why other quantum technologies can't do it. And I am assuming that can't do it means can't reposition their qubits in any way they want. The answer for that is that if this were semiconductor hardware, or superconducting hardware, somebody has to design it one day, and this has to be really printed into something that is, that has all the niobium and silicon and et cetera, et cetera. So once that is done, all that you could do is to create extra wires that you could reprogram the connectivity of the qubits in that way. But that's very complicated. That's done for transistors in something called FPGAs, field programmable gate arrays, but it's very hard and has not been demonstrated for superconducting systems. For ion traps, the situation is different. For ion traps, you get all-to-all connectivity because of the way that they operate. So it technically doesn't make sense to try to reposition things. But you have the issue of having crosstalk and having to coordinate that many degrees of freedom, many modes. I'm not going to say that one is better than the other. I'm saying that there are some advantages and disadvantages to each technology. And one big thing that we play a lot with in neutral atoms is with this capacity, since we are holding atoms in free space, is to play with this capacity to move them around. And that we believe is very relevant.
Some guidelines, everyone. Stick to the policy to ask the questions on Discord and not on Zoom. Pedro cannot see Discord, so he doesn't know that there are 50 questions already. And Vardan is here to pick the right questions and to decide whether to ask Pedro right now or afterwards.
Yep.
We cannot do all of them, unfortunately. Let's do a couple of questions. You mentioned rubidium is used, Pedro, and that it's like hydrogen. Two questions are, why not use hydrogen? And could also cesium be used? Then later a question was, how do you take that image?
So we don't do hydrogen because hydrogen is too light. Okay, so hydrogen would fly away too easily. It's not necessarily the best. Why not do cesium? Actually, no reason. There are some companies that actually do operate with cesium. And there are also some setups. I think that in Chicago, people are studying that to have both rubidium and cesium at the same time in a single platform. So those are all possible. Okay. There was a second side to that question.
Yeah, if you go back to the previous slide with the beautiful images, how were they taken?
Yeah, how imaging is done. So the imaging is done by fluorescence. So you shine some light, and then the atoms that are excited, actually, they don't respond, and the ones that are not excited, they do respond. So technically, there is kind of an inversion of what the machine sees as 0 and 1. We are definitely not going to go into that, because that would just make us confused.
Kudos to Bakao, who already had the right answer. And then what is the frequency of the laser? And do you use one that does not match any of the transition levels?
Yeah, so the excitations here, they are usually 2 photon transitions to get to the Rydberg state. This becomes details that we might not need to cover too deeply. But the Rydberg state, and yes, somebody asked if puffing means putting the atom in the Rydberg state. The answer is yes. So the puffed atom in the Rydberg state, the transition there would be in the UV, the ultraviolet, and it's a nightmare to make mirrors for that. So to avoid that, what we do is we use an intermediate state. We do a 2 photon transition to get there. So usually I think that the main Rydberg lasers, they are 1013 nanometers. No, that's the infrared. So it should be a 420, I believe. If that's a question of what kind of frequency light we are using. So we have 1013s, we have 720s, we have 420s, 780s. We use a bunch of different laser frequencies. Yeah,
fantastic. From now on, Pedro will ignore questions in Zoom. Vardan will monitor the Discord, and some we might also only ask at the end if there is time, because we want to get into the software as well.
Very well. So we'll get there. And we're actually getting close to the software. The software will be, we are going to be playing back and forth on the software side together with the presentation. So to be able to operate these machines, there are 2 things that you need to care for. First of them is geometry. Okay, so if the computer looks like what you want, you need to be able to tell the computer what you want it to look like. So you need to be able to play with the geometry. Again, these are going to be positions in 2D space. The second side of this is going to be, it looks like I'm not seeing my things moving. The dynamics. So how do you make these atoms do things, right? How do you control them? How do you make things happen? That is tantamount to setting up algorithms. So we're going to start with discussing the geometry. So hardware constraints. Let's imagine that I'm going to give you a set of 9 atoms. And I'm going to start by telling you that when we are talking about the real hardware, there is a little error, right? So you can't position the atoms perfectly in a given position. So this little error for us is 0.1 microns. That's the magnitude of the uncertainty of the position of an atom in free space. But I'm going to tell you what you can actually do with the hardware and what you cannot do with the hardware. If you're just operating blockade on a simulation level, you can do whatever you want. But for the hardware, there's actually limitations because this is a physical system. So the first thing that you cannot do is to put atoms closer than 4 micrometers apart. Okay, for like, again, a micrometer is 10 to the minus 6 meters. And there's a minimal distance that the atoms can take, which is 4 micrometers. A second thing that is very amusing here is that there is a space, there's a play field where you can position atoms. So these atoms can be positioned in 75 microns in the x direction and 76 microns in the y direction. And the 76 microns is there to encourage you to make aspect ratios that are elongated in the y direction if you want to make long chains. Okay. The reason for doing that is a little technical. We don't need to go in details about it, but it's related to the fact that the green laser that is shining here has to be uniform, right? So this atom must see exactly the same laser as this atom in intensity of light. And it's actually very hard to do this, to make a laser that is very, very flat in the same intensity across 70 microns. So it's actually, if you position long chains in this direction, all the atoms are going to be seeing the laser, in the direction that the laser is propagating, and they're going to have the same intensity, and that's going to be lead to a little better results if you're looking at a single one-dimensional chains. That's a tricky one. So one more thing that you have to remember is that the atom geometry is flexible, but along the y direction, so atoms will always have to be positioned in flat rows. And these flat rows, they have a distance of 4 micrometers between them. And what I would like to do is to take a minute, and it's going to be really a measured minute, to stop and think about these different constraints, and paste on Discord some of your opinions on where these constraints come from. So I'm going to count a minute of silence so that we can do some thinking.
Multiple people are typing. There are
Lovely.
also lots of interesting questions, Pedro. I think we need to organize an additional Q&A so we can cover also more of the physics.
We'll cover some questions. Don't worry about it. Certainly will.
Yeah. Okay, many answers are coming through. Miguel says constraints from the optics of the laser array. Pink Pacer due to polarization and atom size. Sarah says the minimum distance is designed so they don't interfere with each other. Hussein kind of agrees if they are too close, they might interact and do unwanted computation. Lower distance, the repulsion will increase. Interaction between atoms, van der Waals interaction range.
These are all relevant answers for that question. Absolutely. Does anybody have anything to say as to why the atoms are placed in rows along the y direction? Or along the x direction, however you prefer to see this, right? So every x, all the atoms, they sit in a row.
Yeah, and people are thinking about the laser. Is it actually one laser or their own laser beams? Someone says it looks much nicer.
It does. It can look nicer, yeah.
And control, yeah, how the lasers control the atoms, maximize the number of atoms while respecting other.
Oh, I want to stop on that one. I want to stop on that one because that's an interesting comment. I think well, all of them are interesting, but this is it provides some extra insight, right? So I started putting atoms here. Sooner or later, these atoms fly. Okay, they don't stay there forever, and I have to sort them and create patterns. And I told you that I want to create patterns with up to 256 atoms. That's a lot of atoms. If I have to use a laser beam to move these atoms one by one in place, that would take quite a while. So one thing that we do is to create these reservoirs of extra atoms to the sides and actually bring them in parallel, okay, multiple of them, line by line, so that we can sort more atoms more efficiently, faster. And so that we can reach qubit register sizes that are much bigger than what you would be able to do if you did one by one. So that's definitely this point that was raised off to get more atoms in place is definitely a very key observation here. And it's the reason why we are doing things in rows. Now, it is actually possible to avoid that and to do some systematic sorting that is faster and using embedded systems is something that we are putting together in our machines. So this, in the long term, will be lifted, this type of constraint. But right now, that is an important point. So I don't want us to be talking about theory all the time. So I would like to jump to blockade for a moment, and so that we can start looking at how we put this in practice. Programming a quantum computer for us here requires 5 steps. And by the way, these notebooks, they are self-contained. Okay, so you can read them and follow them at your own pace. We are gonna just touch base a few key points of them. But yeah, feel free to read them and play with them later. They're here for you. So programming, key 5 points. For all other quantum computers, points 2 to 5, like 2, 3, 4, and 5 are the same. Okay, so you have to define an algorithm. For us, we call those time traces, but generally people talk about pulses or gates. Technically, it's the same thing. You have to initialize the register, right? You initialize the qubits. You have to actually perform a time evolution or compose those gates, and you have to measure the qubits. So those points 2 to 5 are the same in every quantum programming system. The point number 1 is a different one. We have to define what the register looks like here. And that's where we are going to start. So to do that, we are going to play with a couple. I'm going to give you a couple functions or objects here in Blockade that are going to allow us to generate systems in 2D space where the atoms can be positioned. The first object that I want you to be aware of is called atom list. So atom list is going to take, as you can see here, a list of positions of tuples. And these tuples are going to be the X and Y coordinates of atoms in this 2D space. This is a physical system. These coordinates, they have units. So Blockade measures this in micrometers by default. So if I put an atom at 0, 0, and here I'm putting an atom in the position 0 in the X direction, Y in the Y direction, and so on so forth. Blockade is written in Julia. Julia also cares a little bit if you're using integers or reals and floats and etc. It will always create the list in the most complex or the largest, type of number that you put here. So in this case, we're putting a bunch of integers, but I have some reals here. So Julia will actually recognize this as a real number, a list of real numbers. And if you create your list, it's in the middle of your program, you hit your head, you forgot what you put in the list, don't worry, you can call the variable, you just dot atoms on it, and it's going to tell you what's the content of that list of atom coordinates. But even more interesting, this is quite abstract, right? So if you put these things, you have to really make sure that you're doing things correctly. And Blockade is really here to help. If you call for your coordinates for your atom list and just run it, it will plot for you automatically the position of the atoms. And I can see that depending on the Julia version, there's some flipping on the y-axis here. This is something that I have to actually file something to fix. But the point is that just by calling the coordinates where you saved your atom list, you will be able to see exactly what you're doing, where you're putting your atoms, and if it makes sense what you're doing. And I will call for an exercise here. So if you look at, are you seeing? Hopefully, you're seeing my screen. Actually, can somebody confirm if you're seeing my screen?
Yes, it's visible, Pedro.
Okay, and if I look at the Adobe here.
Yes, perfect.
Lovely. So you have this handout that you can actually also find in our folder here. So it's called the UDG-MIS handout for future purpose. So this contains a bunch of purple circles that you can assume to be atoms. And we have a square grid here. And what I want to encourage you is to come here in this cell and create an atom list with the positions of these purple dots here for a given register for you, and do your first shift enter trying to run something on blockade. And I actually want to take a couple minutes so that people actually can try to do this. And my recommendation, I don't know if Discord accepts this, but what I would say is for you to run this on Discord or run this on blockade, run your atom coordinate function, get a screenshot and paste on Discord so that everyone can see. And everybody that has access to Discord, please let me know if we are seeing pictures coming up.
Yes, we already see a lot of pictures coming up.
Oh, lovely. That's fast.
And some news for everyone who posts a picture and further requests from Pedro and does the quiz at the end, there will be a QuEra certificate for 2 days bootcamp.
Yes, that is true. I still want to give 30 more seconds just to make sure that people have time to think a little bit about it. And of course, if you don't want to put all the 9 atoms there, put a couple, just get a feeling for how this goes. I don't know if everybody is appreciating the fact that there are no units in this grid, right? So this square could be 1 micrometer in size. It could be 5 micrometer in size. It could be 10 micrometer in size. This is a freedom that the user has. And I think that I want you to start appreciating that, right? That you could make these squares 1 micrometer in size, but then the distance between these 2 atoms is going to be square root of 2 micrometers, which is less than 4 micrometers. And this means that that would be forbidden in the actual hardware. So this kind of freedom is something that you need to start to, it's a feeling that you have to develop, and only by doing it, only by trying, you start to appreciate this kind of subtlety. Do we have a few more pictures popping up?
Yes, we sure do.
Sorry?
Yes, absolutely. We are having a lot of pictures coming up.
Okay, so lovely. I'm gonna continue. People can keep posting. This is for fun. The next step is the following, right? So what if you don't want to generate something that looks like nonsense? Nonsense sometimes has sense, but what if you want to generate something that has structure, right? So it looks like a square lattice, or it looks like a chain or something else. very often for simulations of condensed matter systems or solids and chemistry, but even to do things like a city, sometimes a city lives in a square grid, right? So you want to actually be able to generate large patterns that have some specific structure. And here what we did for you on Blockade is to package another object or function here called generate sites that really enables you to generate these patterns much more easily so that you don't have to put exactly one atom in each place. So you just call a square lattice, you tell that you want 4 unit cells in the X direction, 4 unit cells in the Y direction, and you tell it that you want the lattice constant, so the minimal spacing between the unit cells, to be a scale here, measuring micrometers as always. So in this case, it's 3. And tada, it plots for you a square lattice. And this generate sites object generates an atom list. So whatever you save from generate sites, you can immediately use further down the line on Blockade to do your calculations. And here you can, I don't know, I'm going to call for a honeycomb just to prove that it generates a honeycomb lattice. I don't know if you see that this looks like a beehive honeycomb type of structure. So these are all things that you can do and play with. And I encourage you to do it and use it for the future. So there's another exercise where you just encourage to try to do this. Don't have to worry too much about it. It's a simple one. It's more for, if you're following this this by yourself. But of course, if you want to generate sites, use generate sites to create some patterns. The options are up here, and paste them on Discord. Won't hurt. But meanwhile, I want to take maybe 1 or 2 questions and then move to the next topic. So if we can take questions on the geometry, that's where what I would focus on.
Over to you, Vardan.
Right, Pedro, so there's a question from Nasser. He is actually a quantum researcher himself, and he asked that the constraints over here, the geometric constraints, do they have, I would say, a limitation when we are trying to scale up the quantum computing hardware devices?
So these constraints, of course, they, like every geometric and physical constraint, they are part of what you have to take into account when you're thinking about scaling. The minimal distance of about 4 microns, technically, if you work with us directly here at QuEra, we can push this down, right? So we know how to make this machine suffer, right? Torture it a little bit with, kind lasers to squeeze more atoms in space. But there's always going to be a limit to it. If you get to, I don't think that anybody ever runs anything lower than 2.5 microns, okay? And even at 3 microns, you start to see distortions on the patterns of interactions of the atoms that roughly change the system that you're simulating. So if you want to keep control and have something that's well-defined, we are sticking to about 4 microns. And this also limits the field of view. So you're not going to be able to put 256 atoms in 4 microns apart, all in a single line, right? So that's why I was saying up to 256. It depends on the geometry. It depends on how you're playing with the field of view. This field of view can fit up to 256 atoms, but it's not every geometry that's going to allow you to get there. I hope this answers the question. Can we take one more?
Perfect. There are no more questions right now on Discord because everyone is busy trying to solve and create those images.
So I'm going to interrupt that in any case so that we can move to the next topic because we need to keep going. And the next topic is information processing. So up to now, you're figuring out how to put atoms in place, but we have to know how to actually make calculations happen. And this is just as important. So if we can, I'm going to keep going on. Do you have a thumbs up?
Just a quick question, one just popped up. And the question is that, given the constraints on the geometry, can you still have an all-to-all interaction between the given atoms?
We don't. Wrong. So we don't. This is going to be the topic of the next part of the conversation. But what you see is that the interactions are local, and they are defined geometrically, right? Just like particles that are interacting in space, they are going to be interacting more strongly with particles that are closer to each other, to themselves. Okay, so these interactions are not all-to-all today. We have a new architecture for our future machines. You're going to be learning more about that in the future. It's not going to be the topic of today's conversation, but in our new architecture, the interactions are actually all-to-all. And it's going to be gate-based as well. So, which makes a perfect segue to what I want to discuss right now, which is how do you actually program a quantum computer? Right? So, most of you that have been learning about quantum computing and quantum information processing probably have been learning about quantum gates. You have probably heard of Hadamard's and X gates and C naughts and CZs and all that stuff. And what's happening there is the following, right? So if you want to do a calculation with a set of quantum objects, what you're doing is to perform what we call a unitary operation on them. So if you have gone through the math of that, you know what that means. If you have not, don't worry too much. That means that you are doing some transformation with matrices that are very, very general and satisfy some constraints that are necessary because of physics here. Now, these unitary transformations, they are actually very complicated if you want to do an arbitrary one. And what people have figured out is that you can decompose all of those in a minimal set of rules. And these are the universal quantum gates that you're usually learning about. So when you're saying, oh, I can do single qubit rotations plus C naughts, and that forms a universal set of gates, that what you're saying is that in principle, you can make qubits do whatever you want, as long as you have at least control over those 3, 4, or 5 minimal rules. Those are very nice because it allows you to do very universal programs, but those are very bad because every single of those gates introduce error in your calculation, because such is the nature of quantum computing. Those gates are noisy, those gates don't do what you want them to do. These physical systems, there is some analog behavior because these qubits live in this block sphere that you may have learned. So every time you rotate an arrow, there's always a little bit of that arrow will go. And even if it goes in place, your system is physical, so it dissipates energy, dissipates things. There's noise from the environment. You want to keep it isolated, but at the same time, you want to control it. And there's a very, very paradoxical thing about making a quantum computer, because you want the system to be isolated, and at the same time, you want to control it. So that's exactly where the problem arises. So gate-based quantum computing is what we call here digital quantum computing. It's very universal, but it's not very efficient. And given that today quantum computers are not very clean, we really believe at QuEra that if you want to do something new with a quantum computer, you really need to operate it at maximum efficiency. So yes, we are not going to cover the whole Hilbert space, but what we are going to do is operate this in an analog way. Analog means that we are going to continuously drive these atoms in a way that is natural for them that satisfy their natural operation. This is going to make things more robust to errors, particularly for quantum simulation of dynamics. We don't have to trotterize. If you have heard of that term, we don't need to trotterize because we are continuously driving the dynamics. We follow the dynamics as is. So this is more efficient to errors. It allows us to control less the qubits individually because we don't need to do individual gates on everyone all the time. So this allows us to have few control lines to many qubits. So this means not, sometimes you look at the like a superconducting system, and everybody likes to see that as a chandelier. I like to see it as the predator. I don't know if you're from the Predator time, but it has with lots of hairs coming out, right? So that's something that it's complicated, right? If you want to control every single qubit individually, that's complicated. You need efficient control channels. And this allows you to do single-step entanglement. So you at once you entangle a lot of qubits and you can prepare quantum states very well. Again, the downside is the universality. So no, Aquila is not a universal quantum computer today, but it's very flexible and it can do many, many different things, including discovering things that have never been seen before. That's something that is special about this type of technology. There has been discovery. Not everything that has been experimentally done with a neutral atom quantum computer has also been simulated in a laptop. And if you can simulate in a laptop, your quantum computer is not bringing much for you. So we want to try to live at this edge, at the extreme of that, okay? So are we going to just throw the towel and say, yeah, it's not universal, so swallow it and, just live with that? No, we're actually going to do something about it. We're going to use this flexibility that we have to move the qubits, to move the atoms in free space, to give you an extra knob and change the connectivity of these qubits so that you have an extra possibility to develop new algorithms, to develop new problem-solving techniques that would not be available to you otherwise. So it's a balance, right? We are not giving you a fully universal quantum computer, but we are giving you some new turning knobs that, to say the least, are going to be a lot of fun for your creativity. And these systems where we can reprogram the connectivity of the qubits is what we call a field programmable qubit array, right? It's an array of qubits. You have a field, and we can program them in this field. So if you have some electrical engineering background, you may have heard of embedded systems. You may have heard of FPGAs, field programmable gate arrays. This is the quantum version of that. And this is trademarked. I forgot to add there, but QuEra owns the trademark over this. And if you're convinced that this is cool, we can move on to something that is going to be really, really technical. And I'm going to have to apologize for everybody that has not seen any quantum mechanics, but there is no way about it. We are going to have to face it. It's okay. We are together. We'll do it together. I'm with you. So ask questions. An algorithm, a quantum algorithm, is just the time evolution. It's something that is a processing time. You have an input, you wait, and then you get an output. So something happens while you're waiting. You're not just waiting for doing nothing. You are evolving the system according to some rules. And hidden behind all the gates that you may be used to is some object called a Hamiltonian, this little h here. So if you know your differential equations, this is the evolution equation of quantum mechanics, also called the Schrödinger equation. Psi is your quantum state, and everything here is controlled by a single object that we call a Hamiltonian, and due to Hamilton, we call it H. H, if your background is in computer science, it's like a cost function, except that it's a matrix. And it controls all the energies of your system, and when you look at the energies individually, then you can really think of that as cost functions, really. So what does the Hamiltonian look like? And I've heard this one before. There's no way of hearing a QuEra talk without seeing a Hamiltonian. So here we go. This is what Hamiltonian looks like. There's a lot of jargon and notation here. We're going to go through each of them step by step. First, everything that you see T here, it depends on T, the user has a control over. Okay, so you, the user, will be able to control this. Omega of T, you can control. Phi of T, you can control. Delta of T, you can control. Omega has a term. We call it a Rabi, R-A-B-I, Rabi frequency. It's called that because it's what makes qubits rotate and have Rabi oscillations. Phi is called phase because it's a phase. and if you're used to complex notation, right, what a complex exponential here gives you a phase in complex space. These objects here are the objects that allow for exchange of qubits from ground to Rydberg, from 0 to 1. Okay, so here's a cat, here's a bra. These objects, they means that they are transforming a vector into another, and it's transforming, in particular, a 0 or a ground into a 1 or a Rydberg, and vice versa. So quantum mechanics demands that this object has both options. You have to go and come back, okay? This is also the type of term that leads to X gates. X gates are the things that flip 0 to 1. So this is exactly what these guys are gonna do for us. These objects are generated by the green laser, and the green laser is something that shines over everyone, everywhere, all at once, right? So you see that while there is a little I here, don't confuse this I and this I. This I is just the complex I. This I is just the position of the atom, or a label that identify your atom or your qubit. This omega does not depend on I. It does not depend on I because the laser is shining on everyone, everywhere, all at once. So you don't get to control how much you're flipping individually. The next term, so I'll say again, omega calls Rabi, phi calls phase. The next term is a delta. This delta term here, it operates diagonally in the Hamiltonian. Diagonally in the sense that it operates just on the number of excitations that you have. So if an atom is in the 0, it pays 0. If an atom is at 1, it pays 1 in energy. And this delta is called a detuning. Detuning. It's called a detuning because we detune an atom out of resonance, and that generates an energy cost. This is just how we like to call things, right? So we like to call these things, it's atomic physics jargon, and we are imposing it in the rest of humanity. So sorry about that. So detuning also depends, it's done globally, it's defined globally. In the short-term future, we'll be installing some features that will allow you to control these fellows here a little locally, but that's to come. So keep on the next couple of months and we'll see if this will be ready. The final term is nonetheless probably the most important. These are the interactions. It's a van der Waals type of interaction. It falls with the distance between qubits to the power 6. So qubits that are close together interact stronger. Few qubits that are far apart interact weaker. And you will see that this guy costs 0 if both qubits are 0 in the ground state. It costs 0 if one of the qubits is in the ground state and the other is excited. But it's gonna cost 1 times Vij if both of them are excited. And this is what I was saying about the puffed atoms, right? If one atom is in the ground and the other is puffed, they don't see each other. Vice versa is the same. But if both are puffed, then they can polarize each other and then they will interact. I'm going to take a big break here to take questions because this is physics happening and physics requires questions.
Sure. So first off, there's a comment that this was a really smooth interpretation and explanation of the Hamiltonian. So kudos to that, Pedro. First question up.
Oh, okay.
Yeah, the first question is, okay, so there are a couple of questions related to the previous topic about the geometry of and the positioning of the atoms. So I'll take those first. The first one is that can we do computing and then resort the atoms? So can we try and entangle? Yeah, can we try and entangle the qubits and then physically move them without destroying the entanglement?
No, not today. Not today. That is the next architecture that is coming up. You're going to give us a few more time to set it up. This has been demonstrated in the labs. There's an interesting paper from last year or the year before, no, last year, by the Harvard team, which does this qubit shuttling architecture. And that's definitely in our roadmap, but it's not yet ready. So to be very clear for everybody, you pick where the atoms are going to go, and then you run your calculation. You can't mix that, you know, first you pick, then you run your calculation. You can't pick again. You can run and then you can, restart. When you restart, you can choose your, then it's on you.
Great. Then there's a question on the deuterium part. Can you please explain that again? And then there's a specific question that why the deuterium term is only for the diagonal terms.
So this is just the name, right? So from a user perspective, all that you have to care for is that this detuning controls the energy, the global energy that all qubits are going to have if they were to be excited into the Rydberg state. The process by which we make it happen is doing something called a Stark shift. So atoms under light, their energy levels, they kind of change position slightly, and we can make the resonance with the laser that we are shining go away by doing those Stark shifts. So it becomes technical. I don't want to go there too deeply, but the bottom line is that the consequence is that you are taking a Hamiltonian in a system where the atoms, the global energy is changing, and you can think of this as if it was like a longitudinal magnetic field applied in a magnet. That's this look, for those that have the expertise, this is like an Ising or Ising type of Hamiltonian. This is the delta acts as a longitudinal field, omega acts like a transversal field, transverse field.
Right.
One more.
The next question is about the Hamiltonian itself. Someone comments that it is very similar to the Jaynes-Cummings model Hamiltonian. And then there's a follow-up question on that. How do we actually obtain this particular Hamiltonian? Is there a possible derivation or deduction to arrive to this particular model?
So I will make 2 comments there. So starting from the last one, let me start by just quickly browsing here, QuEra.com. What am I doing? QuEra.com. You can come here, look at our publications, white papers, and there is a new paper here on Aquila, telling lots of details, and this gives a partial derivation of the Hamiltonian. If you want to go in details on this, that's going to take more studying, but you are very much welcome to do it and to contact me if you want to know more. I'm going to paste a link to our white paper that discusses that. The other question or the other comment was that this looks like a Jaynes-Cummings Hamiltonian. I would claim that not really. Okay, so the Jaynes-Cummings Hamiltonian would be one kind of spin, one two-level system interacting with a bath of bosonic modes that could be like harmonic oscillators that have an infinite number of them. This is more similar to a magnet. It's a bunch of, two-level systems side by side. So it's slightly different. Maybe we can take one more and keep going.
Great. One last question I would like to take. It's again on the geometry of the qubits, the placement. Ron asked that, is there a specific geometry which is the most efficient, geometric pattern which proves to be the most efficient for quantum algorithms?
Well, the beauty of this is exactly that it depends on the application. So I'm going to give you some examples in the next session, which we have to move faster to get there. But I will give you some examples of how you can use this in an efficient way.
Excellent. So I guess on that note, please feel free to continue.
Great. Thank you. So same story. There are going to be constraints by the hardware if you want to run a job. So delta, omega, and phi. The first point to notice is that blockade can make smooth functions. The hardware doesn't make exactly smooth functions. It makes piecewise linear functions. The resolution of those piecewise linear functions is so that you can actually be quite flexible, and you can make, for example, sinusoids with many oscillation patterns within our coherence time, which we'll talk about in a moment. but everything is defined in piecewise linear functions. So if you generate a smooth sinusoid on Blockade and you export it to Aquila, the exporting process will break that sinusoid down into piecewise linear function, right? It's going to kind of polygonize it in some way. So this is something to be aware of. Phi happens to be defined in piecewise constant. Okay, this is just a matter of the user, what we expect the users to be using this most for posting. We did it like that. The maximum value that you can do for omega over 2 pi, please don't ask about the 2 pi. It's an emo physics type of thing again. Sometimes you like to think of cycles, sometimes you like to think of hertz, and so there's a factor of 2 pi that keep popping up. So for all that I care, we'll be thinking about 2 pi megahertz. The maximum value of omega is 2.5 2 pi megahertz. Okay. The maximum value of delta varies actually from positive to negative. So it goes from -20 to +20 2 pi megahertz. And the phase, of course, you can wind it around multiple times from 0 to 2 pi. It's up to you. Important, the maximum simulation time. Simulation here, I'm talking about like really the dynamics, right? If you're using a quantum system to simulate another quantum system, but it's of course it's a quantum system. So the maximum runtime is 4 microseconds, and within this 4 microseconds, we can establish roughly 15 Rabi oscillations. So if you are just doing a simple experiment of putting a qubit pointing in the z direction, and then applying a transverse field and seeing it oscillate, we can make it oscillate 15 times within a coherence length for the system. If each oscillation is 2 x gates, right? It's 2 pi pulses, 2 pi gates, where you flip and then you flip back, and you flip up and you flip back. That's one oscillation, right? This means that we are running about 30 x gates of depth within this coherence time, which is quite neat, to be honest, for a system that can get up to 250 qubit scale. So I want to jump back to Blockade and teach you how to do this on Blockade. So here we are. There are 2 new functions or 2 new objects that you need to be aware of. And these are objects named piecewise linear and piecewise constant, and they operate exactly the same way. So to do that, to operate it, all that you have to do is to set up a set of clocks measured in microseconds. And these clocks are going to be the beginning and end in the x-axis for every piecewise segment that you want. The values that I'm putting a conventional 2 pi over there, convenient 2 pi, they're going to be the y values in each of the clocks. So what's happening here? Piecewise linear, clocks 0, 0, you are starting here. We go to 1.5 seconds, and then, well, sorry, to 0.2 seconds, and we move to 1.5 over there. We are here. Now, the next stop is going to be at 5.5 microseconds. It's going to be here. And how much is going to be the value? 3.1. Blockade can do 3.1. Aquila can do 2.5, right? But that's the game. That's the game. If you don't want to play with piecewise linear, you can, as I said, define smooth waveforms. Blockade also has function for smooth waveforms. When you export it to Aquila, it will do the job for you and it will break it down. But this means that you have to be careful with the predictions that you get from Blockade and the actual result of your experiment on Aquila. By the way, Blockade, if you play well with it, 15, 16, you can do on your laptop, 20, you can do on your laptop. If you play with something that's called the Blockade subspace, you can get to 30s, 40s. If you use some HPC resources, you can get to like 30s, 40s, maybe even 50s if you play very hard, and depends on the system size. Okay, but blockade will give you quite fast results for quite sizable systems. And notice that this, well, so piecewise constant also for phi, but this is all. Okay, I want to say this with very, very, very full voice. This is all you need to know. Atom list waveforms, period. After that, I'm gonna show after we take a break. It's just run, and things are running. So you really don't need to know a lot of Julia, a lot of like, it's two functions that you need to know: two objects, atom list, waveforms, piecewise constant, piecewise linear, and you're done. So I'm leaving an exercise for you for later, which is I picked up a few waveforms from the blockade documentation, and this is an exercise in creativity. So the goal is for you to guess what these waveforms would be doing and what kind of problems they would be solving. So I have 3 sets here. If you feel like you don't have the background for it, don't worry. I didn't give you the background for it. This is an exercise in guessing, is an exercise in intuition. Okay, so you can play with it. I would like to propose we take a break. 10?
Sure.
Like until noon 20, let's say, Eastern time, so that we can really calm down. But just to wrap up the conversation, this is something somebody asked: what do we do with the geometry? And we're going to cover this idea of efficient problem encoding for some optimization. So you can make the atoms look like cities and use that in your favor to solve problems. You can actually use this to parallelize, right? So sometimes you have a calculation that's not going to take the full system space. Well, you can multiplex and run several jobs all at once if all that you want is to run smaller systems. And that's the summary of today. We discussed the architecture, we discussed analog digital, we discussed FPQA paradigms, and we discussed some hardware constraints for geometry and waveforms. So I'm gonna leave this on the screen. I'm gonna officially call a break. If you wanna post questions, I can take some questions. But otherwise, please do get some rest because there's a lot of content. Oh, okay. So we're gonna be on a break screen.
Great, break time. And indeed, if there are questions, we can do those in the meantime, but please feel free to take a break. People are taking the break seriously today. That's good. QuEra has kindly offered to offer a certificate for 2 days bootcamp. So if we see that you participated actively today and also did the quiz afterwards, you will get rewarded that QuEra certificate. In addition, a 2 days bootcamp is part of multiple bootcamps, multiple software bootcamps. We will have Xanadu on quantum machine learning. We will have QBraid on quantum circuit optimization. We will have Quantinuum with a TCAT workshop. We will have Terra Quantum on Thursday with solving the traveling salesman problem with QUBO formulation. These are 5 really exciting workshops, and overall they will give you the software certificate from WOMANIUM. Yes, Ron, good luck fixing the QBraid lab. Ricky from QBraid is online also to help out. Everyone is helping each other. This is indeed a good moment to get it fixed. If you have questions, share a screenshot too, so it is a bit clearer and we can help better. Yeah, clarify about a certification for today. This has nothing to do with the normal WOMANIUM certification. That is as explained in the first session. that you can have module certificates. There will be a module certificate for QBronze, if you don't have QBronze yet, a module certificate for QNickel, module certificate for hardware, software, of which today is part, the Global Quantum Project, and a few more. And now, for today, special software edition, there will also be a QuEra WOMANIUM certificate for just today that you participated in this QuEra workshop. And this is separate. So you can get a QuEra certificate for today, but to fulfill the WOMANIUM requirements, you will need to have all the quizzes of all software sessions done to get the software certificate. You will fulfill the requirements for the QuEra certificate if you did the quiz on Canvas, and if we see that you participated actively today. So we see which people are online now, and additionally are active on Discord.
I observe some of the people on Discord having a hard time following the lectures, and believe me, that's completely normal, especially if you do not have a strong background in quantum computing. So I would advise to just take a breather right now, try to follow up as much as you can during the live lecture, and obviously you would have the chance to go through all the material afterwards as well. You need to take the quiz obviously after the lecture. So take your time, go through all the notes, all the GitHub repositories, try to do all the exercises again, then attempt the quiz, and hopefully you will get that.
Some people who just joined this week ask for the link to Discord. This is in your welcome email, the same email where you found the link to Canvas. People who just signed up, you might only have received the Luma link, and the links to Discord and Canvas will follow within the next 2 days. Great that you're joining. We have some really exciting topics this week. And indeed, the bootcamp is on a specific topic and relatively advanced. So take your time to read the further QuEra resources, to take a look again. And we need many, many people in the quantum field from all different backgrounds. Usually, even within the team, the computer scientist doesn't understand all the physics. The physicist cannot engineer all the software. We have electrical engineers, we have mechanical engineers, we need business people. So everyone complements each other, and that is the same now. We don't have the expectation that you understand every single part or can execute everything, but take away main messages and especially be inspired for a new topic.
Hi, Marlu, can I chime in?
Yes, welcome back, Pedro.
Thank you. It's early, we're still 5 minutes early, but I wonder if this is a good time to take some Q&A, just in case there are some people around.
Definitely. Yeah, and some people also ask about a certificate. Can you solve more after the lecture? Yes. Please go ahead, and we will also add this question about showing the graph to the quiz, so you can also share that there and not only on Discord. Vardan, did more questions on the topic appear? Oh yes, coming in now. Bakao, our champion from Senegal and France. You please go ahead, Vardan.
Sure. So the first question is about the imaging of the qubits. How does that imaging take place? And does that imaging have some effect on the fidelity of the qubits, the entanglement of the qubits, and the physical state of the qubits itself?
Yeah, imaging always affects the qubits, and the way that the imaging is done today, it's destructive, and not destructive only on the state, it's destructive on the register, right? So the fact that quantum measurements collapse a state, I think it's no news if you're used to quantum computing, but in this case here, we really stop holding the atoms and we blow them away, right? So the atoms, some atoms stop. That's what happens. That's how the process goes, right? So the light pretty much blows the atoms away. And so every time we measure, we have to restart. And of course, we do have to account for things like atoms that we thought that were not shining, but were not even there. And so these kinds, they all affect the fidelities. But I think that the fidelities are pretty high. I don't have the number exactly right now, but it's like in the 99s, I'm quite sure.
And which particular technique is used for the imaging?
I think that what I mentioned was fluorescence, right? I don't know if there's anything more specific that I can say about that. It's just fluorescence. You shine light and then you collect light.
Right. So another question is there on the nature of the Hamiltonian. Is the Hamiltonian a fermionic or a bosonic Hamiltonian?
So this Hamiltonian, most people will call it a bosonic Hamiltonian. I call it a spin Hamiltonian. It's really a bunch of spins, and it's the closest thing is an Ising model in the presence of a strong longitudinal field plus a transverse field. It's an Ising type of Hamiltonian. So if you want, it's bosonic because things that are far apart, they commute. But if they're close apart, then you have some SU2 issues.
Right. Another question is from Abdullah. He asked that Rabi and laser detune parameters are fixed globally. So is this specific to only Akeda, or is it applicable to all neutral atom systems?
So that's an interesting comment. Aquila is the only neutral atom quantum processor that is public. So it's very hard for me to say what the others can do. Right? We can say what has been reported in other by other groups, academic groups at least. And as far as I can tell, all of them have been globally detuned and globally driven by Rabi. This will change. So we are looking into installing capabilities to enable local addressing of these qubits, at least at the analog level and at the digital level. Right? So, but the digital addressing is going to be very different. The architecture is very different. So stay tuned for that.
Another question is from Miguel from Mexico. He asks that, does the size and the geometry of the atoms array affect the amount of operations that can be done in a single run?
So not really. So the operations, the operations is a 4 micro, you have this window of 4 microseconds, and in 4 microseconds, you do what you want, right? So it's independent on the size of the atom array, et cetera, et cetera, et cetera. You still have your 4 microseconds. And the Rabi maximum is still 2.5 2 pi megahertz. So given that, the fidelity to sort huge registers is smaller than the fidelity to sort smaller registers. So you will see a difference in performance there. But if you're promising that you can do calculations that are meaningful at 256, this means that the fidelities are high enough, right? So we set a bar for what's acceptable, and definitely you can run everything that you can run at 100, you can run at 256. It might require you to generate a little more statistics, but definitely everything can be run.
From Italy, Juliana, a researcher, asks that how do you preserve the state of other qubits when you're performing mid-circuit measurements?
Oh, you don't, right? There's no mid-circuit measurements yet. So the measurement is completely destructive, right? So and it's not only destructive of again, the state, but it's destructive on the register. So all the atoms are blown out. And thanks for asking, Juliana. I actually know Juliana. What you're probably thinking is how we're going to do gates and how we're going to do error correction. That the process is different. There, the process is really, really different because even the qubits are not the same qubits anymore. They're going to be qubits. So the whole structure is going to be different. And then the mid-circuit readout is possible and non-destructive on the register, et cetera, et cetera. But those are things that are in development.
Earlier, you mentioned that this neutral atom is not a universal type of quantum computing. So Victor from Mexico asked that, apart from that, do you have any other weak points for neutral atom quantum computers?
So let me restate that, right? Like, you can do universal quantum computing with neutral atoms. All the structure for that has not been assembled in a single machine yet. But all the different pieces necessary have been demonstrated. Aquila specifically is not universal. Aquila is just this analog machine. But I think I want to separate what's the machine and what's the technology, right? And can you tell me again the end of the question?
Are there any other disadvantages to using
the other disadvantages, right? So things that people usually keep in mind as issues with this, or it's not issue, but or they're kind of not the strongest points, right? So you can see that the time, the scale, right? So the clock speed is not very high. So Aquila will be generating like data at about 3 shots. So three cycles per second, 3 point something. You can get a lot of data out of this. It's a lot of compute power because that's a lot of like 256 qubits. It's a lot, but it's a very slow shot rate in comparison with a laptop or something else, right? That time scale also changes when we are discussing gate-based computing. When we're discussing gate-based computing, the constraints and the speed is different because the operation mode is different. But right now, that's seen as a main kind of weakness of the technologies that. And before we keep going with more questions, I think that we should go a little bit with the materials of the second for the second session. And what I can try to do is condense it a little bit. I think that's not going to be too hard, and so that we can take time for questions and have a more direct interaction. I think that can be quite beneficial, it seems.
Absolutely, we would love to have you again, maybe a separate Q&A session with all the participants. If you are up for it, the participants would love that because Discord is lighting up. There are more than 100 questions right now.
We can arrange for that. We'll talk offline and we will arrange for that.
Excellent. So yeah, on that note, please continue.
Very well. So let's jump to the second part of the session. And this is session usually 4 of my little course. But again, a lot of this can be done in a non-linear way. And today we are going to defy quantum, and we're going to do this in a non-linear way. Joke for the experts. I don't know. So we're going to talk a little bit about how to use what we discussed previously to solve an optimization problem. So usually I would go from there to a kind of more physics applications, because that's the first natural playground. But to keep this receptive to as broad an audience as possible, we decided to move and actually do optimization, which is a topic that has relevance probably independent of what you do in life, right? Sooner or later, you're optimizing something. So what's MIS? And we're going to get there. But first, my favorite part, the learning objectives. I think that it's very important for us to keep track of what's expected from me and from you. So by the end of this workshop or this session of the workshop, you will learn how to encode, let's get a mouthful here, unit disk graph maximum independent set problems in Rydberg atoms or neutral atoms. Sometimes we use the term interchangeably. We're going to go through the definition of what are each of these concepts. You'll be able to determine something called the Rydberg blockade radius and how to think about adiabatic algorithm for optimization. So adiabatic algorithms, sometimes people call annealing. So if you have heard of annealing, we're talking about the same thing. Is Aquila an annealer? No. Can Aquila do annealing? Yes. Right. So I think that it's something that sometimes when we focus applications on the optimization side, people think that Aquila is just an annealer. No, Aquila is not just an annealer. It can do very, very broad and different quantum dynamics. It can do cyclic, periodic pulses. It can do quenches. It can do a lot of things. And it can also do slow ramps. So if it can do slow ramps, that's a very efficient way of doing annealing, of solving optimization. But it can do QAOA. People have demonstrated QAOA with this kind of machine as well. And we'll learn how to write down a blockade code pipeline to solve these maximum independent set problems on unit disk graphs. 3 points. I think we can get there in 30. Let's see. The starting principle here is going to be patterns, right? So let's say I put here a square lattice of atoms, and never mind this thing on the bottom, we'll get to it. And I'm going to drive it. And I want to see what collectively happens with these atoms. So it turns out people have done that. And they have created something that we call in physics, when you're studying phases of matter, we call a phase diagram. Phase diagram, just like you're having water, liquid, solid, etc. And in a magnet, you can have a paramagnet versus a ferromagnet versus an antiferromagnet. You have the phase diagrams of Rydberg atoms in a square lattice. And it's very cute what these phases look like. So for example, if the atoms, so how you read this, right? Let me go slowly. On the x-axis, what you're reading is the detuning. Here they call it a small delta. It's just our big delta that we were looking before. And this big delta is you're going to think of ramping it from left to right, right? So it goes from small to some sizable value. And in the y-axis, you're measuring some degree of the interactions between the distance between the interactions of the atoms. So I said that the interactions depend on how close they are. And depending on what is the energy that I input for flipping the atoms with the Rabi frequency, that's the omega here, I can kind of control how far they see each other. Because if they are very far and I put a strong omega, I can flip. If I put them very close together and I put a weak omega, well, now they can't pay for the energy for the interaction. But if I put an omega that's strong enough, then maybe I actually can overcome that energy barrier. So the distance and the omega and the energies, the deltas as well, there's an interplay there. So y-axis is going to be seeing this interaction distance. So this is what I call the blockade radius. And the x-axis is gonna be the detuning. And what you see is that if I have lobes here, right, that have names, the checkerboard, the star, the staggered. And what does this mean? This means the patterns, this refers to the patterns that we are seeing of atoms being excited to the Rydberg or not in the presence of its neighbors. So here what I'm saying is what? I'm saying that if the interaction distance is around one lattice constant, so it pretty much this atom sees this atom, so the one on the left sees the one on the right or on the bottom, then if I try to excite them, if I try to push the detuning, and I'm going to get there as to why the detuning is doing this, but if I try to excite these atoms, the first neighbors in this lattice are going to be blocking each other. And naturally, what you see is a pattern that's like a yes, no, yes, no, yes, no, yes, no, yes, no. Just because the distance that they are seeing each other is exactly the first neighbor, right? So the first guy blocks the second, and then blocks the third, and then blocks and so on and so forth. But if you increase this distance, you start to see other patterns, right? You start to see patterns where the first guy is going to blockade everyone around it, not just the first neighbor, but also the second neighbors. And then these patterns, they change. And you can start to see all kinds of self-organization of this system, which is very interesting for a physics point of view, but it can also be very interestingly used for optimization. I'm going to give you an example. Let's say I live in Boston, which I do. If you've never seen Boston, this is Boston. Well, technically, everything down to the lower part of this river is Boston. Everything above of this river is Cambridge. And you can see MIT is down here, Harvard is up the street, and there's Boston University down here. So if there's one thing that doesn't lack in Boston, it's universities. And if there's one thing that people that go to universities need, is coffee shops. So I'm going to put coffee shops in Boston, and I'm going to propose the following picture for you. Sometimes less is more. I could put a coffee shop in every single corner of Boston, and everybody would have a place to go. But probably those coffee shops would start competing with each other, right? Like I start to sell coffee, then the other person says, no, my coffee is cheaper. So that's no good, right? If this is a single company selling coffee, we want to put as many coffee shops in a way that they do not compete. So what I'm doing here is creating a condition that says, coffee shops compete if they lie too close to each other, right? I can assume that if they lie right across the street, that's not going to be any good. And if they lie a little farther, maybe not so good. But if they lie far enough, they're not going to be competing with each other, because there's going to be another, like somebody here down in Boston is not competing with down in up in Cambridge. If you live in Boston, you know that public transport is terrible, and you'll never go from Cambridge to Boston just to get coffee. So this network that I'm creating here is just a set of possible points where I could want to place my coffee shop, and the connections would be the distance between these coffee shops at which they do compete with each other. Now, you can try to do this with a gate-based quantum computer. And I'll tell you this. A, you're going to be lacking qubits. Period. You're going to be lacking qubits. It's going to be hard to get enough qubits for that if you are going to try to control every single qubit everywhere all at once. Second, you're going to have trouble trying to encode this geometric constraint. This geometric constraint is a cost in energy that is distance dependent, and that's not necessarily how a brick wall geometry for a quantum processor is encoding. So you're going to have to encode that somehow in your system, and you're going to have to simulate that and do your QAOA on that, and that's going to, I hope you're convinced that is you should not even try to do that. Now, what can you do here? You can make Boston in atoms. And if you doubt that this is Boston, this is the same map, you can, usually I like to show people this motif on the bottom right corner, right? So there's this little branch and this triangle. This is it, right? So the little branch and the triangle here. Get convinced that everything else is in the right place. Right, everything else is in the right place. You just create a set of system that looks like Boston, and just like we were creating a pattern where neighbors were blocking before, I can create a pattern where atoms that are too close block each other, and everything that disappeared is a prime position for me to put a coffee shop. So on the right, you see the solution of the problem. This problem is called the maximum independence set. An independent set, so let's go through the graph theory part of this. I give you a graph of nodes. I paint them white. I put edges between them. And to create an independent set means to paint a subset of these nodes, let's say in red, in a way that connected nodes are not painted at the same time. So, for example, if I painted this guy in red alone, it's an independent set already. No one around it, it's painted red. I could paint this guy in red and this other guy here in red as well. And there is no edge connecting these two. It's also an independent set. The maximum is to find the largest. The maximum independent set is to find the largest. It's typically not unique. So many graphs, they have degenerate maximum independent sets. And actually that checkerboard pattern was the maximum independent set of the square lattice for first neighbor blocking. And that one is degenerate. Kind of, you can flip all the whites in blacks and blacks in whites, and you would get the same thing. You would get an independent set just as well. So this problem is NP complete or NP hard. It depends a little bit how you ask the question, as usual in complexity theory. But we have a system here that solves it natively, right? The atoms, the type of graph is going to be defined by this kind of radius that we were talking about, this blockade radius. So any atom that lies inside this radius of each other is going to have an edge, just like you're seeing here. So I have the blue dot, you have a yellow radius around it, and everybody that is inside, you see that there is a little edge with respect to the blue one. But everybody that's outside of that has no edge there. So this is called a unit disk graph. And then to solve the maximum independent set means to try to get the largest number of red dots so that two red dots are not connected. Just as that. Am I clear? If I'm not, I can take a few seconds for one or two questions.
Absolutely. So there are a couple of questions, and not exactly related to the graph problem, but a bit before that. So there's a question that, can we see that the control of an atom between the ground state and the excited state as an entanglement process?
So the entanglement happens between atoms. Right? So in particular, when you solve this problem here, when you do this, the quantum state that you're measuring is definitely a superposition state that is definitely a very highly entangled state, where the dynamics made everything scramble. And in other words, when you measure, the quantum state after the algorithm, you will not necessarily see exactly the maximum independent set. You will see a superposition of many possible solutions to this problem. And if you do a good algorithm, the highest chance will be on the solution of the problem. So this system will be definitely entangled. We are using entanglements to solve this. We are using superposition to solve it.
Then there's a more general question, I would say, that asks that, can we implement qubits on a hardware?
If you put 3 atoms together side by side, you get something, if they're close enough, you get something that is similar to one-hot encoding, where only one at a time can be excited. And you can play with that to create something that is similar to a qubit. Now, again, I mentioned this before, that our next architecture is actually going to operate in qubits. So we're going to have 2 ground states and one Rydberg state. The 2 ground states are going to be memory, and the Rydberg state is going to be for entanglement. But I really don't want to mix topics right now, so we're going to save the qubits conversation for later.
Another question is, yeah.
Anything on the MIS? I think that I wanna make sure that before we continue, we are on the same page on this.
Right. There were a couple of questions that is similar to the n-queens problem.
Which problem?
The n-queens problem, where you try...
Oh, the n-queens problem. Oh, I like the n-queens problem. I remember having that as a challenge in undergrad. It's similar in the sense that it's a combinatorial optimization problem. And it's probably, you can probably map the n-queens problem to a certain type of MIS. Because if you take one position, then there are others that you cannot. So you can position I don't know if everybody knows the n-queens problem. The n-queens problem is, I have a chessboard that is n by n in size, and I have n queens. And I have to put those n queens in a way that no queen threaten the next or any other. And the smallest solution for that, I think it's in a 4x4 board. I think the smallest solution is a 4x4 board, and usually a computer breaks down at around like 10 or 12 of those because it's too many if you just do a greedy algorithm. So it's related in some sense, but and you can probably map the problems to each other.
There's another question on what is the exact criteria for selecting the atoms for MIS? Is there like a minimum distance, or how do you determine the?
Yeah, so I have a little cheat sheet here, a little cheat sheet. So what we're going to be thinking is that every vertex is an atom, and the edges corresponds to the blockade radius. And which atoms are going to be excited or not is going to be a cost function that is going to be played by the Hamiltonian, which is exactly the topic that we're going to move to right now. Shall we?
Then there's a question, one last question before we move forward.
Okay, yeah.
How do we make sure that the position of the electrons after excitation is the most optimum solution to the problem?
So it's not quite the position of the electron, it's rather the quantum state that the electron is in, right? So we are going to design an algorithm so that an excited state corresponds to, let's say, a position that I don't want a coffee shop, and a ground state corresponds to a position where I do want a coffee shop, for example. Right, so we're going to design things so that that happens. I'm going to show you how. So let's look at it. So we have a Hamiltonian here, and we have our little graph on the left to help us think. So let's look at it. The first point to pay attention to is the last term. Right? The last term is this interaction term. I said that when I have 0, 0, I don't pay anything. When I have 0, 1 or 1, 0, I don't pay anything. But when I have a 1, 1, I pay V in energy, and this V depends on the distance of the atoms. So this V clearly corresponds to the condition of I don't want atoms that are close together to be excited together. Let's say that the red means a 1, right? So I cannot have a 1, 1 if the atoms are too close, because I'm going to pay a Vij that in the limit of atoms touching each other would be divergent, would be way too much. Make sense? So interactions precludes a global mutual excitation. Okay, I cannot excite everyone all at once because of this interaction. Then we can look at this other terms of the Hamiltonian. So let me start with delta. So delta is very interesting here. If you notice, delta carries a minus sign. And what happens when delta is very, very negative? If delta is very, very negative, we can use our intuition about energy, right? Like a roller coaster. I always want to be in the bottom of the roller coaster because that's my point of lowest energy. So the system is the same. It wants to be in the lowest energy. So if I put delta being very negative, this number becomes very positive because there's a minus sign. And the smallest energy will be when, again, H measures the energy, right? So the smallest energy will be when all the M's are equal to 0. Because every N that I put is multiplying a big number in front. I don't like that. So this guy here in the bottom pushes all the atoms to stay in the ground state. All the vertices are white. Now, conversely, if I try to push this delta to very, very positive values, I will want as many N's here as possible to be equal to 1. Because I'm going to have 1 plus 1, 2 plus 1, 3 plus 1, 5 plus 1, you know, 200, until all of that multiplying minus a delta. And that's going to lower my energy. So I want everybody to be excited if delta is large. I want nobody to be excited if delta is large negative. But even if I push everybody to be excited, V precludes everybody to be excited. V says, if you're too close, you will not be excited. So this is looking good. This looks like it's doing what we want. Now, if you're firm with our quantum mechanics, you will notice that if there is no omega, a product state of everybody being 0 is going to be an eigenstate of this Hamiltonian. And as I evolve this delta from negative values to positive values, that eigenstate will remain an eigenstate and nothing is going to happen. So what we are lacking is scrambling. So we turn on the delta so that the atoms can start flipping, and that's where all the superposition is going to happen. We're going to start mixing the states. And as long as we know that we are pushing this slowly, we know that by construction, the state where delta is in the end, the Hamiltonian where the Hamiltonian with the final delta will correspond to a Hamiltonian where all atoms want to be excited under the constraint that Vij is not going to let all of them to be excited exactly with a specific connectivity. So I go from a ground state to another ground state as long as I go slowly, and the final state, if the final Hamiltonian corresponds to a Hamiltonian whose ground state is what I want, we are in game. But how do we define this connectivity? That's what I've been sweeping under the rug so far. I have not told you exactly how to. So I've told you that there is this radius, and I've told you that it's possible to fix this radius according to some energetics, but you have to learn how to do it. So let's see how that goes about. This is a tricky business. The first tricky part of this is that this radius is not unique. So let's take these 4 atoms here, and let's imagine that they're actually dots. Okay, so just so that I'm making them big so that we can read. I could pick a radius for blockading the first 2 neighbors, that is this one, or I could pick this one. They're kind of touching, right? So I know that I said that they're supposed to be dots, but you know, give me a break here, right? Like this is for concepts, right? So I could pick either of these 2 radii, and I would be blocking exactly the same atoms. How do I decide? Well, let's start with the geometry first. You have to make a pick. There's no sugarcoating this. Like, you will have to make a pick. It's a decision. It's a life decision, a commitment that you have with your life. You know, it's like, sorry, you have to make a decision in your life. And this is it. We're going to give you an empirical rule that we figure out that works well for this. You do the following. First, you look at the atoms that you do want to block. And you look at the smallest possible radius. And now I'm going to think that these are really like point particles and that I could not take anything smaller than this. So I'm going to call that R min. Then you're going to go and I'm going to look at the largest radius after which I start to block atoms that I don't want to block. So in this case, it's the second neighbor, right? So this is first neighbor, this is the second neighbor. And then I'm going to do the geometric average. Usually, if you follow this process, it's a good idea. It works well, gives you like a consistent way of doing this. Empirically, it works well. Can you do something else? By all means, you can use this as a research project. Figure out if there's a better radius, a better choice for radius. Can you do some machine learning to figure out a better choice of radius? You know, the sky's the limit. But this is just the geometry part. So this is measuring angstroms. I need to convert angstroms in, like I told you that the user can control delta, everything that depends on T. You have to convert this on megahertz somehow. The process for doing that is to look at this Rydberg blockade paradigm. I'm going to look at a problem with just 2 atoms here and no omega, just to keep it easy. And I'm going to look at this V12. So this V12, I told you that it goes as 1 over R6. The coefficient that goes above it, we call it a C6. You don't have to worry about what it is. It's just an overlap integral. It has a number. It's fixed for Aquila because the orbitals that we use are fixed. If you look at what the Hamiltonian looks like for these 2 atom problems, it's actually diagonal and quite simple. It looks exactly this. So whenever I have 1 atom excited, I pay delta. Whenever I have 2 atoms excited, I pay 2 delta. And when I have 2 atoms excited, I pay V12, and everybody lies in the diagonal. If you look at the energy landscape of this as function of the distance between these 2 atoms, what you see is that 0 remains 0 independent of the distance, minus deltas also remain degenerate over there. But this state here with 2 items excited, it ramps up. Whoa, right? It ramps up because of V12. And at the point that this guy crosses minus delta, you can just equate -2 delta plus V12 equals minus delta and solve for the distance and find what's this distance here. And this distance is going to be our blockade radius. So all you have to do is to ramp your delta so that it ends at the corresponding blockade radius that you want. And that's going to give you the graph that you want with the connectivity that you want. So you have to match that geometric distance RB with a final value of delta that has to lie inside of the -20 to +20 megahertz that Aquila can do. And that is going to give you the correct graph. This is not easy. I'm going to show you how to do this on blockade, and hopefully that's going to make this a little better. So this is how the algorithm goes, right? So you have this guy. I'm going to make the delta ramp. I'm going to make the omega ramp as well so that I can have some scrambling. Usually I always push omega to the largest possible value. It's just a kind of, it sets a speed of oscillations. So this kind of sets the real clock speed of my Hamiltonian, of my system. And the final value of delta is going to be determined by this formula over here that we just saw where it comes from. So let's take a look at, do I want to, no, I think that before I do that, I want to give you a challenge. I'm gonna give you a challenge, of course. Where would I go without the challenge? You still have that handout, right? This handout, so that we play a little bit with our intuition. The goal is to draw the MIS corresponding to this graph, under the constraint that the blockade radius is that thing in red. And if you have this printed, I encourage you to just paint, show on your camera, take a picture based on Discord, do your thing. If you want to paint on my screen, that's also allowed. You can annotate. And I'm gonna give you a couple minutes.
Could you explain it once more, Pedro?
Absolutely, absolutely. The goal is to draw edges between the vertices in a way that respects the, well, first of all, draw the edges between the vertices to figure out what's the graph. And second, paint the maximum independent set that you can see for that graph. Sorry, I maybe was not too clear about that. Yeah, it's a two-step process here. Where's my annotation tools here? Let me see. Oh, I cannot annotate on my own screen. Yeah, looks like I cannot annotate my own screen, so you're gonna have to do it for me, if you're allowed. If you're not allowed, then we're gonna have to just show pictures.
I will take over screen sharing, Pedro, to show some of the questions,
absolutely.
some of the pictures.
Absolutely. Go for it.
There are some questions. How much blockade radius do we consider?
So we consider exactly the red circle.
Great. Is there an example of the task in the notebook?
There will be, we'll get to it.
No, this is the first image that is emerging.
Right. So let's look at the first one. Let's look at the first one. So you see that if we sit on the first atom here, right, the distance of the blockade radius is in the diagonal, right? It crosses exactly the diagonal. So this first, yeah, exactly. Those two are definitely connected. But now when you look sitting on the first one on the top left and go all the way moving to the right, that one, so this is too far, right? Do we agree with me that this is too far? Only the second, the diagonal here is being connected. So definitely that's the connectivity is too large over there. Let's look at the next one, because I think the next one overcame this difficulty. So this one got the first two correctly, but I think that it didn't get the next one correctly, right? So if I'm seeing this as a sort of point type particles, then you see that the second neighbor here is definitely too far from it. So I would claim that that this is not quite what we are looking for. Also, another point, you see that you drew on the top two, the top two red ones, you see that there's a connection between them. So if they're connected and we're looking for a maximum independent set, they cannot both be painted, right? So let's look at another one. Let's see how we're doing. Oh, come on, one up. Oh, so okay, some people are moving fast here. They're doing this on blockade already. Stop. Let's not go so far. This is done on blockade, but you are getting independent set, but not the maximum one. And if you can see that this is not the maximum one, you see that the node 6 could have been painted. Node 6 could have been painted. So this becomes an algorithm problem or post-processing problem. But yeah, if you look at this from down, above. Oh, okay, this one, yeah, you got it fixed. You got it fixed, Vlad. That's it. I think that we got one here. I hope does it. Okay, this is a very dangerous question for an audience of 235 people. But do we understand why this is a possible answer? So we are still missing that the bottom 3 are inverted. So this is still not the maximum. This is called a maximal independent set. It's an independent set that you cannot add another node, but it's not the maximum because it's not the largest.
So can you summarize once, Pedro? How is this independent, and then how would it be maximum? So
it's independent because you see that nodes that are connected by an edge are not painted together, right? So you see a good example is the top left, right? You have 2 nodes. There's a gray little edge, and only one of them is painted. So this makes this red node a member of an independent set because there's no other red node painted close to it. And the same applies to every single red node that you see here. Now, this is not the largest because on the bottom right, you could have not painted the red one and painted the other 2. And you would have gotten 1 extra. We game? We got lots of options. Yeah, now Sorana got one that is in the ideal. And you can see, right? Can we stop at Sorana's solution over there? You can see that on the top left, you could have inverted, right? You could have not painted one and painted the other, and the size of the solution would remain the same. So you can see that this is degenerate. There's more than one option. Let's move on and see how we could do this on blockade. Can I control back? Thank you for trying. This is very exciting to see everyone, you know, making your efforts and getting there, and the process of learning. So this is very, very pleasant for me to see. So we had stopped here, and I would like to jump to the actual MIS notebook. So let me give you I'll just explain how I'm doing this, and then I'll leave you as an exercise to do exactly what we did right now. So I'm going to start by generating a graph to solve the problem. It's not the same graph that you were looking at. This graph is going to live in a square lattice that I'm going to randomly drop 20% of the atoms. And I'm going to give a distance for these atoms that is about 4.5 microns, which is actually acceptable on Nakula. And the type of problem that I will be looking for, I want to create a system where I will have connectivity on the first neighbor and on the second neighbor. So on the sides and on the diagonals. So this is what we usually call a king's graph. King's graph because it looks like chess. You know, the king can move in chess, it can move in the diagonals and into the sides by one step. Right. So since there's some things missing, we call it the defective king's graph. It's the graph that is defective, not the king, right? So this is the graph that we're going to be looking at. We have to define RB. So I'm going to follow exactly what I said to you. I'm going to look at the minimal distance that I can block, and I said that I want the second neighbors here. And if this distance is A, this distance is square root of 2 times A. So that's what you're seeing here. R min is going to be square root of 2 times A. The maximum distance after which I don't want to block is going to be the third neighbor, right? So this would be the first, this would be the second, 1 to 2 here would be my third neighbor. And the distance is 1A, 2A. And now I'm going to take the average, and that is going to be the geometric average. So square root of 2 times square root of 2A. And you compute that, you get 7.76 microns or something. Blockade is very nice to you because you can call blockade plot, and you can put your atoms, and you can call blockade radius. And you can see if what you're plotting, if the graph that you're determining with that radius is the graph that you had in mind. And you can see that in our case, it is. So I can see that I see connections between the first neighbors, vertically and horizontally, and you can get second neighbors diagonally. So these are what a defective king's graph looks like. Then what do we do? So this is the block. This is the block. We just used our atom, well, we didn't do atom list, we used generate sites. But that was the first lesson from our first session. Now we have to use the second part, which is the piecewise linear, and we have to determine a few protocols. So I said that the maximum value of omega is 2.5 megahertz. So that's what I'm setting up here. And I'm going to ramp delta all the way so that the final value of delta is going to be C6 divided by RB to power 6. So let's look again. I'm just going to invert this equation. I take the 6 power, I put the delta up, I take the RB down, and I get my value for delta. So once I fixed RB, I can fix delta. And you can see that this is exactly what we learned. Okay, so it's just piecewise linear, and you're just giving some clocks. It's exactly what we did before. The things that you have not learned and that I'm going to teach you now, you have to put those things inside a Hamiltonian. So how do you do that? You call a function called Rydberg H. It's going to eat your atoms. we defined the atoms up here, atoms. So it's going to eat an atom list. And it's going to eat some waveforms. A waveform omega equals to the omega that we defined here. A delta equals to this delta. A phi equals to this phi. Then you have to start the problem. So you have to initiate all, from H kings, you're going to initiate all the qubits of H kings on the 0 state. We're going to simulate this for a time equals to Tmax. We're going to give it what's the Hamiltonian in its H kings. And you have to, this is a differential equation that is going to solve. So Julia has many libraries. Here, what we want to use is something called Schrödinger problem. It's just a choice. And I'm going to run it, and I'm going to emulate the problem, and we're going to take a few seconds. It's more than I want, less than it could be. It's going to do it. I have no fear. I trust blockade. Okay, it did it. Notice that this has been a problem of 13 qubits that was just run in, does it say? I forget here. Maybe 10 seconds or something, right? It was pretty fast. So it's a quantum dynamic simulation of 13 qubits, right? It's not just a calculation of ground states. We are not just diagonalizing a Hamiltonian. We are doing the simulation, the time dynamics of this. From the problem, we can extract the qubit register, ask for the 10 largest probabilities in that register, and plot a histogram. And this is what you see. So these are the bit strings that compose that state. So remember, this state is a linear superposition of many, many possible states. And one of them is very, very big, and all the others are much smaller. So this is already indicative that we have created structure, right, in our state. We are giving preference to a state over others. We can test against the solution. So we can paint on the graph, and this is the solution this is the highest probability solution. Okay, so I'm getting best bit string item 1. This is exactly this guy. Lo and behold, right? This is the maximum independent set, actually. You can see that this is an independent set because 2 red dots are not painted side by side. You can see that this could be the generate. This 13 could be the number 8 here. But I could not paint number 7, 11, 6, 3, 4, 5, 9, 12, nothing. You know, I could shift some positions. This is the generate, but this is it. So our algorithm does what we expect it to do. You can look at the second most likely solution. And this is something that is cool about quantum, right? That you get many possible solutions from one calculation. And what you see here is that 2 flipped to 5, and the second most likely solution is also a maximum independent set. So we can sample from the list of maximum independent sets by doing this, which is a different problem in a different class of complexity and just as hard. But if you look at the third one, what you see is that this is not a maximum independent set. It's still an independent set, but it's not even maximal. Okay, I could put more. And this is a lesson for the future, right? That among all the states in the quantum superposition, some of them will not be the solution to your problem, which is natural. Can you make this better? Yes, absolutely. You can do some machine learning to improve the post length. You can do some non-machine learning. You can just do some physics and figure out better post lengths. You can try to do QAOA instead of adiabatic algorithm. There are many things that you can do. You can try to improve by hand. There are many things that you can do. But I'm going to leave you with an exercise, which somebody already did. Which is to take the handout, generate an atom list out of that handout with a distance between the atoms that makes sense, and run this algorithm. Most of this is going to be copy-paste. So everything is really helpful here for you. And I don't want to stop sharing. Trigger happy. I just want to mention to you a few more interesting points. First of them is that we did a very, very in-depth analysis of this problem with a team at Harvard last year. And we showed that this is a little hard to read, this plot, but we showed that we figure out what's the hardness parameter that classifies if a graph like this is difficult or easy to solve. And in the hardest instances and large instances, we can actually see a scaling of the chance to solution using the quantum computer that is different from what you would get using a simulated annealing, just a classical annealing process. And the improvement, so this is the difference between the blue and the red curves here, lines. The improvement is pretty much a square root, which is exactly what you expect from Grover search. It's a Grover type of speed up. So this is something that you can see in these neutral atoms. The coherence is there, the quantumness is there. And no, you don't need to use this to solve easy problems. You shouldn't. Quantum computing is not made to solve easy problems. But for hard problem instances, you can get some non-trivial results here. And this is something that we find that is very, very inspirational, and that makes us hope that we can bring this to deliver something useful in some specific optimization problems. And we have actually many applications for independent sets. There's a paper over there that you can look for that I did with my friend Jonathan here, Jonathan Wirtz, looking at variations of this independent set. So there are maximum clicks and other types of logical problems, graph problems that live in the neighborhood of independent sets, and that how they can be deployed for antenna placement, for placing stores like we just did, for routing. So you can make something for routing, you can do something for antenna, for 5G type of technology, ad hoc networks. We have recently learned that you can do this for chip design, VLSI chip design. We have recently learned that this can be used for satellite mission planning. So there are many, many applications of this maximum independent set problem that you can look at. Sometimes they're going to be geometric, sometimes they're not. There's a lot to think there, but that's the summary. So maximum independent set, don't forget that we can make hardware efficient encodings. So this flexibility is something that is very interesting in the hands of the user. What an adiabatic quantum algorithm looks like and how you define basically the end of this algorithm, that's the most important part, which you define via the blockade radius. Remember that quantum matters, even when it's not quantum matter. And remember that we have many applications. I'll leave you with our learning objectives so that you can revise, and with the mindset of how we think of MIS with our type of systems. And we will call it a day for today's tutorial.
Excellent, Pedro. Thanks a lot. If you would wait a couple of minutes more, there are a lot of questions popping up on Discord.
Yeah,
so
I hope so. Do you want to bring some questions?
Yes. So the first question is that the way between the states, should they be linear in time, or is there another path which they can follow?
Can you ask again? I'm not sure I fully understand the question. I think that this question is about these figures.
All right. So the question is, the way between the states must be linear in time.
I see. So you're talking about the, I guess the person is asking about this trajectory here, if it needs to be linear. And the answer is no. Okay, so in fact, when we did the work with Harvard, we did a closed loop optimization between the hardware and the quantum hardware and the classical optimizer to figure out better paths. If you look at the documentation of blockade, you also see, let's see if I can share, no, this one, and then I can go to blockade. No, blockade. And we can just look quickly at the documentation here. If you look at the tutorials, we have some tutorials on maximum independent sets, etc. And you see given a specific application. So here is some optimization being done. And you see that, look, an optimized path may not be fully linear. It might even have some non-trivial slowing down when gaps are closing, speed up when you get close to the end, and some application here for chip design also. So this is actually a quite handy feature, and it's all on blockade documentation.
Great. So there are a lot of comments coming in that it was a great session, excellent session. For some, this was actually the first quantum software bootcamp. They're just high school kids and they're really enjoying that. But coming on to the question, there's one question that asks that, do the algorithms which paint these vertices with the least degree, do they have some kind of a hypothesis? How do they work?
I'm not sure I understand the question.
Okay, let me rephrase that. How does the algorithm, or what hypothesis do the algorithms use while painting the vertices with the least degree?
So I'm not sure if they're, I mean, the main hypothesis is that the atoms interact according to that energy function that I was giving you, right? That's the main hypothesis. But when you're building an algorithm, you really need to think like a few atoms. What are they doing? You know, as I ramp things up or down, what do I expect to happen? And how do I use that to solve a problem? And those, there's a little bit of art there that is really dependent on the user. I don't know if I have a more concrete answer than that.
There's another question on the application side. Someone asked that, are there any applications of neutral atom quantum computing in neuroscience or biology, for example?
Very, very interesting question. So last year and even this year, we have been looking a little bit on those. So we're definitely very interested in applications in biology and biotech. There's a lot of the process of genetic alignment when you're doing some pretty much analysis of genes. Right? You take a DNA strand, you unwrap it, you chop, you multiply, and then you have to piece that thing together. You analyze the things the little pieces, and now you have to piece things together again. Some of that is used use methods of finding maximum clicks, which are kind of clusters of completely connected subsets of nodes in a graph. And those can be, in principle, solved using this kind of approach. There are some questions about what would be the value of doing that. Are we looking for like more precise genetic sequencing or faster? So those are open questions. What is even needed? And what is the power that a machine will need to have to actually solve a physically meaningful or biologically meaningful problem? But there are definitely questions in biology. I can imagine also predator-prey type of networks. I can imagine many, many applications.
That's super exciting to hear all these applications. There's a question from Ron from Chicago. He asks that if an MNIS solution produces 2 or more maximum choices, can an additional matrix be added via the software to pick one of the best top choices? Maybe something like service loading or edge counts?
So you can definitely do some post-processing on the data if that's exactly the question. I hope I'm understanding it correctly. But yeah, the answer at the end of the day, I think it's yes, you can do that.
Perfect. There's another question on, now I guess you have already answered this one, but just to reiterate the point, that can you still create some sort of a digital circuit using blockade?
So so 2 points. Point number 1, at a large scale, QA/OA is something that people do with digital quantum computers that can be done with blockade. And I want to emphasize, we will not have time to do this, but you can export jobs from blockade to Aquila. Okay, so whatever you run on blockade, you can submit to the real quantum computer as well. Now, I have some colleagues that are working with us from a DOE national lab that got overexcited, and they started to generate gates with this, and they wanted to play and see what kind of 2-qubit gates they can do. So the answer is yes, you can just put 2 atoms together and generate an entangling gate and generate a CZ gate, or yes, you can play with that. I don't know if it's gonna take you very far, because this machine is not made for that, but who knows?
Great. So there are a lot of questions popping up. I would like to take another one. What is the driving being used to drive the system? Is it microwave driving?
It's not a microwave driving. In the next next architecture, it's going to be there will be some microwave, I think, for some Raman pulses, but this is really optical range, mostly optical range.
Mm-hmm. And a couple of people on Discord are really excited when you mentioned that there are new machines coming up from QuEra. So they really want to know when would the next iteration or the next quantum computer would be launched, and when would they get to learn more about that?
Well, when I talk about this topic, I say that I can tell you what's our roadmap, but I will not tell you how fast we are driving. Okay, so TBD. I know what are our plans. The plans is soon, but I am not allowed to give anything more clear than that.
Coming back to the questions on the technical side, there's a question that how many vertices and edges can you put on a graph maximum?
Right. So if the encoding of the graph is perfect, an example, placing the stars in Boston, right? So every vertex corresponds exactly to one star. Then the maximum is 256. Right? It depends a little bit on the geometry that you're using, but the theoretical maximum is 256. And again, the user can make smaller systems or bigger systems, right? It's a choice. Now, there are situations where, remember, somebody was asking about Q-treats, and I was saying, oh, maybe you can put some 3 qubits together, and then you generate this thing that people call one-hot encoding, where only one atom at a time can be. So now you can kind of decorate your graphs and imagine that now instead of having two choices, you have 3 choices, and you want to pick only one. So it's possible to play with this kind of, we call them gadgets, and we have a paper on gadgets as well, to encode more complicated graphs. But and that will certainly incur a cost in number of atoms, and that will make logically your problem smaller.
Another question is on the FPGA systems. You briefly mentioned this, but the question is, how can FPGA systems develop the neutral atom structuring?
We use that a lot, actually. So one example for this is in the sorting part of the algorithm. So if we take a picture of the image and send it to software to start to figure out where we have to move the atoms, to compute, right, what are the trajectories, that takes time. And the way that a picture is taken, it's kind of rasterized. So technically what we can do is start imaging positions, and as soon as we pick up where an atom should go, we can have like your FPGA system already start calculating and start deciding where we are going to be moving and coordinating the atom movement. So this process of shuttling atoms and moving them apart, that's something that definitely can be improved, sped up by FPGAs. And we have quite a few FPGA engineers here, embedded systems engineers, that do that.
Now, most of the lecture are comprised of the graph structures of how to structure and arrange these neutral atoms. But a couple of people on the Discord are really fascinated and curious. Are 3D arrays, 3-dimensional arrays of neutral atom possible?
So There are some groups that have reported being able to sort 3D arrays. My understanding is that in 3D, the third spatial dimension, the control over the waves of the laser is so kind of rough that the atoms end up so far apart that they cannot entangle. So you can't really do much with 3D. Also, you should ask, what do you gain from 3D? And we have done some analysis, and it seems that you don't gain that much, while we are keeping this this constraint of local geometry, right? Unit disk constraint. What will be happening in our next generation of machines is that the atoms will be able to move during the calculation. And now the connectivity is all to all, and now there is no 2D, 3D anymore, right? This lives in infinite D. So, everybody talks to everybody. So this is not even going to be necessary. I would not worry too much about 3D. I don't think it's going to matter.
There are like a lot of questions popping on Discord, and it's difficult to like field all of them today. So I would like to end this Q&A session with a more optimistic note and ask a more general question. Where do you see QuEra? What are your next steps? What are the current problems you're trying to solve?
So we have quite a few problems lined up. Some of them in the aerospace industry, some of them in the energy industry. And as these problems wrap up, and we are going to be making announcements of what are the things that we have done, and they're quite exciting. So energy and aerospace have been big clients. Finance is coming up. We are working hard on quantum machine learning. So we have a method for quantum machine learning that can actually work, that can actually be used on real quantum hardware. I think that that's the strong claim that we'll be unveiling more about it later in the year. Because quantum machine learning, if you just do on circuits, you have these barren plateaus, and that really doesn't go anywhere, as far as I understand. So this is something that we're excited about. And it's a method that we can, at least at a simulation level, we have seen that we can classify not only binary, but we can classify digits really to 10, up to 10, which is something that I believe no one has demonstrated with quantum systems yet. So that's going to be exciting. And we are moving strongly towards being able to do gates. It's something that now we have a system that is large. And I think that that's where maybe, as I said, let's finish with a strong note, right? How do you build quantum computers? How do you build quantum computers? So most groups that we see around, they're building quantum computers by making a universal qubit that can rotate as much as you want, and putting 2, then putting 4, and then making 8. And the question that we have started asking is, do we think that this fault-tolerant universal quantum computer machine that doesn't exist yet, is it going to be simply the sum of its parts? What we see in the industry is just that you try to create copies larger and larger of a system with the same control mechanism, the same control architecture that you had for the small system, and you have this Zeno paradox where you get slower and slower and slower in maybe actually being able to make progress. We are taking a different approach. We have a system that is large and a control mechanism of this dynamic moving of atoms that we can now start elaborating layers of complexity and making this more and more universal and more towards fault tolerance at scale, so that we are not caught by surprise when we try to multiply things by 2 and figure out that our fidelities, we can't reach what we need. And that's how we believe we should be building quantum computers, and that's what we are doing. So Aquila is an analog machine. You should see Aquila as a first step. And the next thing that you'll see is a big step in controllability and the capacity to make general controls over a system that is very large. And that's what we are looking at. And that's how we think that we're going to make the way on the quantum industry.
Oh, wonderful. Glad to hear that, and we are really, really excited of the new news maybe QuEra would be releasing soon. There are a lot of questions, and we hope that we'll see you very soon again for a specific Q&A session. But if that's not possible, what I could do is just jot down all the questions, send you by mail, and you could just answer them and share with me again. We could share them back with the participants.
Yeah, we will make something happen.
Absolutely. So again, a pleasure to have you here, Pedro. Thanks a lot. The participants gained a lot of knowledge. It was the first software bootcamp for the WOMANIUM program as well. So amazing stuff. It's been a busy week for the participants as well. Yeah, again, thank you a lot. Thanks a lot, Pedro.
Thank you, everyone. And it was a great pleasure to me too. So good luck, and hope to see you, in the future. See what you do. Take care.
Thank you, Pedro. This was really an awesome session, and we look forward to hosting you in the hardware panel as well, and see you back there.
See you then. Cheers.
Thank you. Great session. And we have many more really great sessions coming up this week. Tomorrow is all about superconducting quantum computing. We will have the CEO of Oxford Quantum Circuits speaking, Ilana Wisby, who will speak about quantum entrepreneurship, diversity, and you can also ask her anything about what they are doing in the company. Then we will have the main hardware lecture on superconducting quantum computing. This lecture will be guided by the DiVincenzo criteria, about which you learned yesterday. It should be accessible to everyone. Then, after learning about the theoretical concepts, we will dive into a really exciting lab tour, the lab tour on superconducting quantum computing by IQM. And there, 3 IQMers will be there to answer all of the questions. So Q&A will be an important component. While tomorrow is hardware, on Thursday, we will dive into the software again. This will be a somewhat more advanced topic, solving the traveling salesman problem with QUBO formulation, and will be hosted by Terra Quantum. Terra Quantum is a great partner of ours and also a sponsor of this program. So we are really grateful to them. Headquartered in Switzerland, but meanwhile going global also in the US and elsewhere. Then on Friday, we will return to hardware and look into photonic quantum computing with Ulrik Andersen from the Technical University in Denmark. This will be including a virtual lab tour, and it is not all for those of you who prefer software. We will actually host QBraid with Kanav and Ricky, our also great partners. QBraid has been a platform partner for us since the very start. We've been collaborating on many items, and they will show how to optimize your quantum circuits. Extremely useful for anything you will do in the future. That is not all. This session also several people in the program will offer mentoring sessions. Tomorrow, 9 AM ET, that is 1.5 hours before the live session starts, Hussein Gokal will offer a mentoring session. Hussein is the chairman of QWorld in UAE. And on Friday, Emin Akpinar will offer a mentoring session on QNIGGLE.